So the next speaker will be Neeraj Pandey, and he'll be talking about from desktop to browser, creating a browser native game engine with WebAssembly. So let's welcome Neeraj Pandey.
Alrighty, good afternoon, everyone. Great. So, how many of you have worked with games in Python? Like, give me a raise of hand. Perfect. I mean, pretty much half of them. So, and how many of you have tried to change those games to something to work on the browser? Lovely. So for all those who haven't tried it before, in this talk, we'll be getting into the same thing, how to break free from the desktop apps or the desktop constraints and work on the web with a blazing speed, like native speed kind of an environment. So real quick agenda, we're going to talk about what WebAssembly is, what are the challenges we see in bridging those games from your desktop versions to the browser. We're going to talk a little bit about the Pygame basics, and we see how Pygbag, the package manager, is going to be used and convert those games to work on the browser. And eventually, we're going to be converting those games to work on the web. Righty. So, how many of you know what WebAssembly is? Perfect. So the definition says WebAssembly is a binary instruction format for a stack-based virtual machine designed as a portable target for high-performance web application. In simple terms, you can think of it as a secret sauce which makes your high-performance web apps these days. You can think of it as a universal switch which translates your code written in any kind of language, be it C, Python, Rust, or any other one, and just like convert into a compact binary format that browsers understand and run at native speed. Which doesn't mean we're replacing JavaScript, but we're going to be working in sync with JavaScript because it provides an interoperability which makes you work with those web APIs. And the web use cases are like diverse. We can have computationally intensive video games, 3D engines, complex simulations, all can be done by writing pure Python and running it on your browser. So before we go, we should go through a quick overview of like how Python execution flow works. Then we're going to contrast on how the WASM execution flow works in a similar manner. So when you talk about Python, we write a Python source file, which is your normal .py file, which is a human readable code which all developers write. And it's then compiled by the Python interpreter, which reads the source code and converts it into a bytecode for efficiency. And bytecode is simply a intermediate representation. It's not the machine translated code. It's something in between, which is a set of instructions which the Python virtual machine understands. And it's very optimized for the execution and serves as a low language or the low level performance independent version of your code. After the bytecode has been translated, it's stored into memory. Or if you're using some sort of like a modules or like importing those modules, it's going to be stored into your cache, which is going to be your PyC files for quick execution, because we don't want to reorganize it again and again and load them again and again into the memory. And after that, it goes to the execution for the PVM, the Python virtual machine, which is a part of the Python interpreter, reads those executed bytecode and instruction by instruction, line by line, whatever you call them, and it produces the program output. Pretty straightforward how all the Python code works. But now, when it comes to WebAssembly, it works in a very similar manner. We write our source code, be it any language, it doesn't have to be Python. At compilation, the source code is compiled into a WASM bytecode, very similar to how Python bytecode works. And it's, again, pre-compiled into a binary format. And once this bytecode is created, it is stored into the WASM module. And what this WASM module does is it contains all the instructions. What is the data? What is the metadata? What to do with it? What are the execution methods for this? And this is then allocated to the WASM runtime, which is again allocating the memory as a linear memory. So it's a contiguous block of memory. What's happening is like the memory is not static. So memory can just like keep increasing from 1 megabyte to 4 gigabytes if it's required. And so the read and write operations are happening there. And once those operations are done, it's executing and the program output is running. And similarly, when we're working with the browser, it's very much the same. only, you will see that it's happening in a sandbox environment. The runtime and the linear memory is writing into a sandbox environment. Why is it necessary? Because it creates an abstraction so that like makes it more secure. Your code don't have direct access to the modules you're working on outside of those functions. And apart from it, it's also directly talking to JavaScript. So it's because we can't directly make WebAssembly do things in the browser. We need to make sure like we are directly talking to the web APIs, and that's where JavaScript comes to the picture. And we load the packages, you're doing some sort of like a conversation, you're manipulating the DOM, and after everything is done, your output is just like being retrieved, and the program is resulted outputted on the browser. And why this execution flow matters? So these are two of those particle simulations which has like 1,000 particles moving under like gravity. Each particle has a position, velocity, and we update it every frame by frame. I think the internet is pretty slow, but doesn't matter. The main objective is to see like how the performance works. So when you run the same simulation in a Python desktop version of Pygame, it took like 6.3 microseconds for the average frame time. And when it was run on the browser using WebAssembly, it reduces by half. Same thing happened with the particle update speed. So it was like 0.16, and it literally increased by twice. And the CPU usage, which was 95%, has been reduced to 45% now. So now, when we move from a typical Pygame environment to a to browser, what's happening is like the WASM is using the JIT compilation and the GPU acceleration, making the animations more smoother. It's also freeing up those resources you're just like working with because there's no garbage collection happening on the browser. And it also uses like a manual memory management. So it has a linear memory, so it's much, much faster. And what are the benefits? High performance is number one. It almost works at a native speed. If you're working with a core, a Rust project, or the Python thing, it's going to be working at the same speed in the browser. And it's sometimes when you're working with 3D objects and 3D manipulation graphics or something on the browser, it can even be 10 times faster than what your normal JavaScript code must be doing. Second thing is portability. You write once, you make it work everywhere. So it works on mostly all the browsers. Security, as we discussed, it runs in a sandbox environment. So it has very limited access to the system resources. So it's very safer than the native plugins or extensions we keep on using. And interoperability, it has a seamless integration with existing JavaScript and the web APIs. So you can make use of both the worlds, WASM for the performance and JS for your feasibility. And when you work with Python, it's a very same thing we just discussed. So this just like tells you like how the conversion is happening, the Python bytecode, WebAssembly bytecode is happening, and then the Python code, the bytecode is loaded into the browser using a package manager. Normally in Python, when you work with like PyScript and all, it's Pyodide, but like we're gonna touch the Pyodide a bit. But Pygbag, which is the main the Pygbag which we're gonna be using is the package manager. It uses scripting behind the scenes, so we're also gonna talk about that. And it's executed in the WASM environment, and yeah, that's pretty much it about how WASM is working on the browser. That takes us to Pyodide, like how Pyodide works. So we just saw like how WebAssembly unlocks the Python's potential in the browser, but this is another key player when you're working with data science projects or working with NumPy computations and all. So what's happening is like it directly enables your code to run in the web browsers with a very little to no, this bottleneck kind of a thing. And again, Pyodide is this port of a C Python interpreter, which enables Python to run directly in the browsers without bloating. And yeah, it also has direct access to scientific stack, which is NumPy, Pandas, and all those things, which again makes it run at a near native speed. So there are like 4 major characteristics of how Pyodide works. It allows running it to directly in the browser or in the server without the need of a server. It supports the scientific libraries, which you'll be seeing how NumPy functions can be used directly in the browser now. And it's done by compiling the C Python, so it's pretty fast. And if you see on the right hand side, this is the diagram which shows like how the process is going to work. The first step is your JavaScript, which is the web browser, interacts with your Pyodide, which is again triggered by a user input or a script you're working on the browser or on the DOM. Then you have a Python interpreter, which is the Pyodide here, which uses a pre-compiled Python interpreter, which has already been converted the code to WebAssembly, and it then runs your code in the browser. And Pyodide can also load the packages, let's say NumPy or Pandas, that are pre-compiled to WebAssembly. So one thing is like they are not fetched on demand. So they are fetched on demand, but they're not compiled during runtime. So which again makes it much more faster. And again, the execution is it's like the results you're going to be getting is directly going to be working with the web APIs and JavaScript and your Python functions. So eventually anything you see on the browser, it is. I mean, you don't have to worry about like how NumPy has to work, how Pandas has to work. You can directly manipulate those DOM variables, which will eventually be talking to your NumPy functions while you are on the browser itself. So a quick syntax overview of how Pyodide works. So the first thing is you call the load Pyodide function. You use the await asynchronous function because when you're working in the browser, which is a single-threaded way, you want to make sure that your app or your game is not stuck or not hang over there. The second thing is like this is a very simple Python execution function where we're using the pyodide.run Python. We just like printing that statement hello world, which demonstrate how a simple Python command can be run. And then you have the package loading. So you can simply use Pyodide and load package NumPy. This will just like load your package. Then you can import this package and start working with those NumPy functions. And then you can also like talk to your JS DOM. You just have to call like the globals. You just set it with the JS variables and pass in the JS value. Yeah, that's pretty much how Pyodide works. And this is a small example where we are calling the NumPy function. So how we're doing is like, again, we're calling it an asynchronous setup. We use the function is called use NumPy. And we are initializing it with await load Pyodide. Very simple. We just like loading the package. Then we are calling a function which is going to be returning an output. And we're simply importing the NumPy, import NumPy as NP. We are creating an array. We just like calculating the mean and the standard deviations, and we just like logging it out. And this small function will make NumPy work on the browser. And when you actually have to put that code snippet into your browser, you have a embedded script tag within your HTML body. You put this entire script into that function. And the only difference is you have to call those NumPy or the Python functions as a string literals. And that's pretty much it. So now if you click on the run button, which is again an image listener happening on the browser, you click on it, it's going to go call the function. This function is going to import the NumPy library and run the matrix manipulation over there. And why it works is it compiles and executes this Python in the Pyodide format, and it also handles your outputs. So any print statements or error will directly appear on the browser console. You don't have to go to your own Python console and just like make sure everything is working. And if everything works correctly, you will be able to run this thing. One more thing, you will have all these files in the presentation itself, so you can maybe work around with this after this presentation. You call this thing, you have an event listener which is listening to this button, you click on it, it's calculating 3x3 random matrix and calling the determinant and just like printing it directly on the browser. So finally we are at Pygame. So Pygame is again one of the most like the widely used Python library over the years. It's very ideal when you're working with 2D games and very interactive application, not very much with 3D. And it's been since like 2000 or something, and it has been a very go-to choice for like the hobbies game developers in the Python economy. And for those who don't know, Pygame is just a wrapper which is on top of the SDL library, which is a simple media direct media layer, which is again a way to get access to the low level audio, keyboard, mouse, joysticks, or graphics hardwares via the OpenGL and the Direct 3D. And Pygame basically started as a replacement for the stalled project called PySDL project, and it's cross-platform nature. So you write it in one setup, you can run it in another one. The key features are you can render the graphics, you can work with your sounds, you can provide your WAV files, your egg files, you can manipulate the keyboard movements, the mouse movements, you can move those objects, you can add those characters. And one of the last thing, or the most crucial thing, is the game loop, which is basically the building block of your game, how your game is working. So it pre-processes your user input, it updates the state. So we also want to make sure, like, if a character is at one point, after like 2 minutes, it should just like move if there's a key movement happening. And it also makes sure like the game doesn't hang. So this is like one of the most crucial things which we'll be seeing in the next few slides, like how game loop works. And yeah, so let's see like how Pygame works, and then we'll see like what Pygbag is and how we can just like combine them and then run the same game in your browser. So it's pretty straightforward. You initialize the setup, you import Pygame, but the only thing is like you also have to initialize with that Pygame, because we have separate initialization functions which are included in the Pygame modules. And since these functions are like those abstractions for specific hardwares, maybe your joysticks or keyboard or so on, so you want to make sure you initialize with that Pygame so that like it can eventually work with the same code on Linux, Windows, and Mac. And eventually you have something to draw on, so you have set your mode into a canvas. Then we have a game loop. It's a continuous loop which just like makes sure your states is happening, how you redraw, how you blit it's happening, how you flip it. So those are the things we're going to see, like how crucial they are in setting those screens and removing those screens out of the picture. Then we have event handling. So it also allows you to work with your event handlers, just like your JavaScript does. You can make sure like if there's a key press happening, if there's a mouse movement happening, how the characters is just gonna, how the characters is gonna trigger on the basis of those event handlers. And then we have rendering. It also allows you to create your own shapes. Instead of just like copying some characters like a Mario game or something, you just like import that character. You can also create your characters directly as a canvas thing. So you can create circle, maybe a couple of circles, a rectangle, and create your own characters kind of a scenario. And so from now on, we're going to see like how we're going to build up this game, we're going to say. And this is again shows like how you import the Pygame and the display model, how you can display those images, how you're going to import those displays and images and sounds. So you can simply call the image.load, call the PNG, and set it as the main character of the game. You can also add some sounds whenever maybe a collision is happening. You want to have some different sounds. So you can initialize all those sounds at the same time as well. And the last thing is handling events and updating events. So this is something which is new, we didn't discuss. It's called like we can flip the display. So what it means is like maybe at one point of the game we completely want to change the scene, what is happening. So we can simply, after maybe the game loop has closed, we want to say game over. So we can just like flip the scene and everything will be erased. So all the older buffer values will be replaced by the front one, which are the new buffer values. And so the last 10 minutes we're going to see like how we're going to create this small snake game, which most of you might have played when you were like kids or something. So to begin with, we're going to be setting up the game window, which is again exactly what we just like saw previously. We initialize Pygame, we call the initialization function, we create a canvas by 800 by 600 pixels. We are also adding a clock so that like we can make sure we can have the control of the frame rates. So we can say we want a 60 FPS kind of a frame rate or 120 FPS. So you can also make sure like you can also like control those things. And I think the last thing is like we're also defining a small rectangular player, which is going to be a small rectangle just for example. And second thing is like the game loop again. So it updates the positions of the game objects. It also checks for collisions, which you'll see, which is very crucial when you're working with Pygame or Pygbag. It also flips the game or updates the game. The only difference between .flip and .update is .flip changes the entire screen. With .update, you can work with different components. Just like unit testing, you can just like take different components of your screen or your play or the game, and you can just like make it change. And we also like changing the clock speed to 60 FPS so that like we have much more smoother animations happening on the screen. We don't want a snake to move just like suddenly just like going to another place and just like disappearing and appearing. So that's why we are changing with the frame rate as well using the clock function. And then we have the event loops or the game loop. So the game loop will continuously keep on running unless you pass in some parameter, some conditional statement which makes sure like, hey, this is where you need to stop and the game should be get out of the picture, and you want to say do something, and do something could be change the display. Maybe once the game level is done, you want to make it to another level. You're gonna flip the entire screen and make it move to the other one. And you can also add movements. So you can make work with event listeners like your keyboard movements, your mouse movements. You can change the coordinate just like your 2D Cartesian plane. You work when you're working with 2D graphics or 3D graphics. And you are also rendering the fonts like game over and what kind of color you want to give it to it. And this is something you see is like sometimes you don't want to flip the entire screen. You don't want to make this entire old buffer go away because you want to keep that state up and running. So instead of just like flipping everything, you can also blip it. So what blip does is like instead of removing the old buffers and adding the new ones, it number one, it stands for block transfer. So it blip to another surface while the previous surface is still there. So your code or the state is still gonna be staying there, but like another state is gonna be taking over. So yeah, so to blit or to flip, blit draws images, text, shapes, or like back buffers, or in short term, you can say it's a temporary memory you have, and you don't have to update the screen, but you want to make some temporary changes on top of it. Then you have the flip or the update function, which completely changes that scenario. It swaps your buffer back with the front one, so it's in the queue. There's a back one. It comes up on the top of the previous one and covers it up. So in short, it's updating the entire screen, and it's very essential when you're doing double buffering and you want to make sure like there's no flickering happening, or there's no black screen happening, or it's not displaying every single thing at one place. So you want to make sure the game is happening one level, it goes away, another thing come up, or maybe you have something to ask from the user, you don't change the state, you add another one, you blit it and you remove it. Another thing is like in Pygame, we can also do collision detection. So we also want to make sure like how, if you have played games like Mario, you make the player move, it touches something and there's something increment happening. So we have those functions in the rectangular function itself, or the circle hash map strategies. How it works is like it makes sure like whenever two shapes are just like colliding with each other, it could be either rectangular shapes or circular rectangular, different thing like a paddle or a ball, and it makes sure to identify those collisions and gives you back the metric, and you can make sure you do something on top of it, something which you'll be seeing. And if you run what all we see in the last few slides, it will turn to be a very simple squares which just like moving on the screen. Again, the internet is pretty slow, and you just like touch it, you blit it, the game is over. You didn't change the entire screen. So that brings us to the last topic, which is how we now have a game in Pygame, now how we can use a package manager like Pygbag and make it work on the web. So Pygbag uses a custom C Python build, which is optimized especially for games. And how it works is it bridges the gap between your Python game development and the web development. It enables developers to create your application which runs both on your desktop and your web. So it's not like you're making a game which is only going to work on the web. It's going to be working on your the desktop version, but when you build it, you can also make it run after converting into WebAssembly and everything. You can make it work on your browser as well. So just like a Pyodide, Pygbag also relies on Scriptum. Not on Pyodide over here. So it relies on Scriptum, which is used to compile your Python's runtime, and STL, which is a simple direct media layer. And yeah, it makes it compatible to work with most of the modern browser, almost all of them. The second important thing, it helps you with asset management. So what it does, it creates a virtual file system in your browser itself. So you can think of it as like a local temporary thing, which efficiently makes your packages comes and do it as a web delivery thing. And the last thing is it has this asynchronous adaptation. So Pygbag implements asynchronous event loop to make sure your code and everything works in the browser event-driven environment and nothing just like breaks in between. Oh, yeah. So the final thing is like Pygbag acts as a code translator, converts your Pygame code to WebAssembly, and it's a universal thing, works on all browsers. Package managing is done, asset packaging managing is done. It also works as a web wrapper creation. So Pygbag serves as a Git wrapper. You can think of it. It generates your static HTML and JavaScript files, which can then be translated into a package asset. So you can have those translated files and directly run them into the browser without having even a server kind of a thing happening. And yeah, it also sets up a mini environment in the browser, so that you don't rely on something like your own server on the cloud or something like that. And it mimics what your Pygame environment is doing on your local system or the local desktop version. It mimics the same thing in a very mini amplified way into your browser. How do we adapt like Pygame to Pygbag? It's pretty simple. You don't have to do much. You just have to replace a few things, and the most crucial things are you change your update functions to flip, because when you're working with the web, these things comes to lag a little bit more, and because you don't want to swap your entire displays again and again, so flip is the most efficient way you can work with it. Second thing is your asynchronous game loop. Anything you're working on in Pygame, you just convert into asynchronous functions as a main game function, and it will make it work with Pygbag, because web browsers again are single-threaded and event-driven models, and the page might become responsive if one of the function call has stopped working. And the third thing is, there's also like the asyncio.sleep function. So why we're doing this is because we want to get the yield or the control of the what status is there on the environment we're running on. So we want to make sure like we pause the game momentarily, maybe in fractions of seconds, and allow other tasks to run, so that like there is a very overall responsiveness and there's no lag happening into your browser. And the last thing is your event handling. Ensure there's like non-blocking. So everything is asynchronous. You're not using update, you're using flip. You're making sure like you have control over the time, and you are giving proper pauses in between. You don't have to do anything else. You just build with Pygbag, and your normal Pygame, which has been working in a browser, will be converted into bytecode into WebAssembly and will be loaded to the browser. And anything asset which is still on the browser will be directly loaded using the web APIs or JavaScript. So the final piece is like just to go through. It's the same thing. It's just like binding up everything. We have the main loop, which is defined in an asynchronous function. We're calling the asyncio.sleep to get the yield or the control over the browser. How do we want to make game to interact with it? And we eventually run this thing with the asyncio.run main function to start the game. And then this will simply create a small rectangle. And the last thing is, before we see the actual snake game code which we're working on, is how Pygbag function works. So similarly, it starts with your the Pygame code you've written, and then Pygbag is a package manager, so it directly takes your code, makes use of Unscriptum, a tool chain which we use to convert your code to WebAssembly. And then once you have converted this code, you can run this code directly in the browser, but it can also help you talk to your JavaScript, so that like maybe you want to work with some sort of like a DOM manipulation functions. You can directly glue those with the JavaScript code. You can also call in those packages. directly in your browser in the DOM itself, and it eventually creates those static file which we just discussed with HTML and JS, and then loads those games and assets all together. And eventually you have a bundle of all those things, and once you run your game in a static environment, or maybe you just want to run your Python environment as a browser thing, you can run it and the game will be running in the browser. And yeah, that's pretty much it. So this is the last few slides, which just go over to the same code. You initialize the game. We have the game loop structure where we specify the game logic. We have event handling, how you want to make sure your key presses are working up and down, left and right. And if that happens, where should the new rectangular position should be? And this is the code for the collision detection. So we also want to make sure, like, once there is a collision happening, we want to split the game, we want to flip the scene, we want to close the entire game loop and everything. Or if we are eating up those food, we want to again at a random position create those food again, so that like now the snake has to go further up and just like find that food to increment its like value or the length, you can say. And yeah, these are the drawing functions which you're using. You can manipulate this as much as you can. This is a very simple example how we just like create those rectangular filled with colors. And yeah, this is the last thing, which is your Pygbag entry points. So you create those functions, you call it into a main function, and you just like run it as an async.run, and your game will start running in the browser. And if you do everything correctly, if everything works, you will have a small snakes game up and running in a browser in a local host, and you can just like make different iterations of it. And that's pretty much, folks. Thank you so much for joining, and yeah, I hope we learned something new, and yeah, happy to have some questions now.